Hey guys, so this is Module 4, Lesson 22, page 123. So this lesson we are going to compare quadratic functions, square root functions. We're going to see them represented in equations, tables, graphs, and just answer a couple questions about the different forms of these functions that we can see. So we're going to work the first two questions together, and then you will have to do the problem set on page 27 and 28, and that's also posted on Schoology, the directions for that. If you have any questions, let me know. Okay, so it says to solve each problem and then show or explain how we found our answers. So this question we're going to be giving a quadratic function equation and a quadratic function graph. So this word problem says Xavier and Charlize each threw a ball straight up into the air. The relationship between the height, which is the distance from the ground in feet, of Charlize's ball with respect to the time since it was thrown is given by the function s of t equals 16t squared plus 79t plus 6. So this represents Charlize's baseball that she threw straight into the air. The graph of the height as a function of time of Xavier's ball is represented by the graph below. So this is how Xavier's ball was represented. So Charlize, we were given an equation, and Xavier, we were given a graph. So it's a lot easier to find pieces of a function given a graph. So for instance, right now I know that this is my vertex. I can see that these two are my x-intercepts, but given an equation of the function, we're not able to find those things as easily. Okay, so we're going to have to rearrange the equation in a different way in order to find these pieces. So the first, basically what we're trying to figure out is it says that Xavier claims that his ball went higher in the air than Charlize's. Charlize disagrees and wants us to answer the question and support answers. Okay, so we know how high Xavier's ball went into the air because we have the graph. So Xavier's ball went, the highest point is the vertex, which is also his maximum. So this is Xavier's maximum, which is the highest that the ball went in the air. And so Xavier's ball went 75 feet in the air. Okay, so that's easy. His is done. But now we have to figure out how high Charlize's ball went into the air. And so in order to do that, we can rearrange the formula by completing the square to get it in vertex form, which is going to allow me to find the vertex to see how high hers went. So we want to complete the square for Charlize. So her function is negative 16t squared plus 79t plus 6. And so when we complete the square, remember we need this, we need a to be equal to 1. So we're going to divide everything in our equation by negative 16. Okay, so when we do that, this becomes s of t equals t squared, because negative 16 divided by negative 16 is t squared. And then we will do 79 divided by negative 16, and I'm going to change that to a decimal. And so when we divide it, we get negative 4.94 t. And then the 6 divided by negative 16 is negative 0.38. Okay, so now we want to move our c to the other side. So we are going to add 0.38. And remember, this s of t we can set equal to 0. So this is, we're going to add 0.38 here. So we get 0.38 equals t squared minus 94t. Okay? So now that we've moved this 0.38 to the other side, we need to add our magic number here and here in order to make this a perfect square trinomial. So the way that we do that is we're going to do b divided by 2, and we're going to square it. So b divided by 2, we have negative 4.94 divided by 2, and we square that. And when we do negative 4.94 divided by 2 squared, we're going to come out with 6.1. So then we're going to add 6.1 to both sides. Okay, so when we add 6.1 to both sides, we're going to use this space. So 6.1 plus 0.38 comes out to 6.48. So we have 6.48 equals t. And remember, we can rewrite this as t minus 2.47 squared. The reason why we write this as t minus 2.47 squared is because this is our perfect trinomial. So we can bring our variable down. We can divide b by 2 to get negative 2.7, and then we can square it. And so we don't want to solve for t, so we're going to move this 6.48 back to the other side. So we get 0 equals t minus 2.47 squared minus 6.48. And then since we divided everything by negative 16 at the very beginning, we're going to multiply that negative 16 back in. So we get 0 equals negative 16 t minus 2.7 squared. And then negative 6.48 times negative 16 comes out to a positive 103.7. Okay, so now that we have this in vertex form, we can find her vertex. So remember, vertex is our h and our k. So her vertex, when we take the h out, we have to flip our symbol. So this is a positive 2.47, and then our k, which is 103.7. And so remember, the maximum, the height, which is our y value. So Charlize's height is 103.7 feet. So that means that Charlize is correct. So her ball went higher in the air than Xavier's did. Okay, then we have to figure out how long each baseball was airborne. So the airborne factor is going to come from how long it took the ball to go into the air and how long it took the ball to come back down to the ground. So with Xavier's graph, we can look here and we know that his ball left the height, it started at 0 and it ends about here. So we can say that his ball was in the air for about 4.2 seconds. So Xavier's ball was in the air for 4.2 seconds. Okay? And to find Charlize's airborne amount, so if we think about what it means to be a vertex. So the vertex lies on the axis of symmetry, which means it is symmetrical and it basically cuts the graph in half. So this 2.47 seconds is how long it took in order for the ball to reach the highest point. And so it's going to take, since it's symmetrical, it's going to take that same amount of time to come back down to the ground. So in order to find Charlize, her airborne distance, we can multiply the amount of time it took for her to reach the maximum height times 2. So we can do 2.47 times 2. And so when we do 2.47 times 2, we get that her height was 4.9 seconds. And so her ball was airborne for a longer time than Xavier's, which should make sense because her ball went higher in the air than his did. So if her ball goes higher, naturally it should take longer for hers to go up and come back down. Okay? So answering part C of the same question, we need to construct the graph of her function. So we already know what her vertex is. So we know that her vertex is 2.47 and 103.7. Okay, because we already found that. But we also need her x-intercept. So her equation is already in vertex form. So remember, it was 0 equals negative 16 times t minus 2.47 squared plus 103.7. And So to find her vertex, we can solve this equation to find what our two t's are. So we're going to subtract 103.7 from both sides, and we get negative 103.7 equals negative 16 times t minus 2.47 squared. Okay? Then we want to divide by negative 16 on both sides. And so when we divide by negative 16, we're going to get 6.48 equals negative 16 times t minus, that 16 doesn't go there. We already divided by it. And squared. So then we're going to square root both sides. So the square root of 6.48 comes out to 2.55. And remember, whenever we square root, the square root and the square cancel each other out. And when we take a square root here, we have two numbers. We have a positive and a negative. So we're going to have a positive 2.55 equals t minus 2.47. And we're going to have a negative 2.55 equals t minus 2.47. Okay, so we're going to add 2.47. So negative 2.55 plus 2.47 comes out to negative 0.08. So our first x-intercept is negative 0.08. And then our second one is when we add 2.47, 2.55 plus 2.47 comes out to 5.02. So 5.02 is our second x-intercept. So now that we have the vertex, which is way up here, and our two x-intercepts, we can graph those and we can get a rough sketch of what her graph looks like. So her vertex is going to be basically in between 2 and 3, because this can round to 2.5, and up 103.7, which we'll say is about there. So we'll say that's her vertex. And then negative 0.08 should be about the same spot that theirs started, because remember they start at the same time, around the same height. And then her second y-intercept is 5.02, which is a little bit past the 5 mark. And so remember, this needs to make an upside down U shape. It should not make a V. So when we graph this, it should look something like this. So again, her time is longer. It's longer because she threw the ball higher in the air than Xavier. So we have compared the equation and the graph, and now we have turned the equation into a graph so that way we can better see what's happening here. Okay? All right. The second one is talking about science class. It says students constructed pendulums of various lengths and then recorded the time required for the pendulum to complete one full oscillation. The results are displayed in the table below. It says Jack looks at the first 3 rows of the table and says that a linear function should be used to model the data. Based on the data, do we agree with him? And we have to justify. So remember, in order to be linear, linear functions have slope. Okay, so we basically need to see, does this function have a slope? Does it have a constant rate of change? So, remember, to have a slope, I have to add the same thing over and over. So far, we add 5 all the way down until we get to this 30 and 50, and that's when I add 20, 50 and 75 is when I add 25. So this changes, but 20 and 25 are factors of 5, so it could even out over here, but let's check. So 0.45 plus 0.60 is adding 0.15. 0.60 plus 0.75 is adding 0.15, so we're good so far. But then when we add, when we go to 0.75 to 0.88, we're going to add 0.13, and then 0.88 to 1 is adding 0.12, so then we have, we're not constant anymore. So that means that this function cannot be constant, so it's not linear. There is no constant rate of change. Okay, so Jack It just reminds us that it's important to check all of our data, not